To me, optimization is sort of the grand finale of Calculus 1. It's sort of the really big, exciting conclusion of why we talk about derivatives. It gives it a really practical meaning. It's one of my favorite sections here. Optimization is the process of finding a maximum or a minimum value of a function, depending on what we're trying to accomplish here. So all of the problems that we look at today, we're going to be looking at through a practical lens, right? We'll be looking at word problems, applications problems. So we'll want to do things like maximize revenue or maximize profit or minimize cost of materials or things like that. So the first thing that we're going to have to do is find the function that we're optimizing. The two that I recommend that you know that we'll be using quite a bit here are R equals X times P. Remember, that's revenue equals the quantity times the price, and profit equals revenue minus cost. These are two that I would absolutely have memorized. They are two that we're going to keep coming back to. This is a business calculus course, so I like to ask those kinds of questions. The other thing that we need to keep in mind here is we are going to have to find domains for all of our function. And the domain here, I just want you to think about it as what makes sense for our problem. So a lot of the problems that we'll look at, like x values can't be negative. I can't have a negative quantity of something. So sometimes it's as simple as that. We'll talk about them. We have two possible cases for our domain, though. The first is if the domain is closed, so if we have A to B containing both of the endpoints, and in that case, we're using the extreme value theorem, which is what we did in 4.5 in the last section. So we'll find our critical points, and then we'll check the y values of the critical numbers and the endpoints. So that process should hopefully be pretty fresh in our minds from section 4.5. If the domain is open, A to B, so we're not containing our endpoints, then we kind of just have to hope that we really only have the one critical number, because like we said in the last section, we said it's a lot harder to draw conclusions about open intervals when you're talking about absolute extrema. So we kind of just have to hope and pray that we have exactly one critical number. And if we do have exactly one critical number, then we can use either the first or the second derivative test. It's really up to you. I will probably use the second derivative test a lot just to get some practice in, just because it's newer, we haven't seen it as much. But for most of these problems, you can continue to use the first derivative test if you are more comfortable with that. I always just say use whichever you feel more comfortable, use whichever you think is going to be easier. So let's just jump right in. Let's look at some examples. I have a fence is to be built to enclose a rectangular area of 800 square feet. The fence along 3 sides is to be made up of a material that costs $6 per foot. The material for the 4th side costs $18 per foot. We want to find the dimensions of the rectangle that will allow for the most economical fence to be built. So here, I think the wording is a little bit tricky. We want to find the dimensions of the rectangle, so that much is clear. For the most economical fence to be built. In all of these problems, we want to either minimize or maximize some quantity. So when I think about most economical fence, I sort of think that's a fancy way to say the cheapest fence. So what I want to do is I want to minimize the cost of this fence. And we'll come up with a function for the cost here in just a second. For now, this is a pretty visual problem, I would say. We're talking about a rectangular area here. I would recommend drawing a picture. For some of these problems, especially when we're working with area and perimeter, I think that drawing a picture is incredibly helpful. So I'm going to draw a picture of a rectangle, but I'm going to make one of the sides a different color here, because it tells me, it says 3 sides is to be made up of a material that costs $6 per foot. So let's say all of the blue sides right here, that is going to cost me $6 per foot. Per foot. And then that red side right there, we'll say that that is the $18 per foot for that fourth side. 18 per foot. And we should probably give these variable names so that we can talk about them. We don't know the dimensions, that's what we're trying to find, so that'll also help us talk about these. How about we call this x and x, and then the other dimension I will call that y and y. So okay, we have our variables. The first thing that we want to do is write a cost function. I want to write the function that we're trying to minimize. Sometimes this is called the objective function if you want to sound really smart in front of your friends. So I want to minimize cost, so I'm trying to write an equation for cost. So the cost equals, well, I'm going to look at each side. So this is, if I look at this side for just a moment here, this is x units long, and how much does that cost me? That's $6 per foot. So the cost of that side would be $6 per foot times x feet. Same thing over here. I have a fence that is x feet long. It costs me $6 per foot, so the cost of that side would be $6 per foot times x feet, so 6x. And of course I'm going to add those two things. Actually, let me make this blue just to avoid any confusion. This side right here is y units long, but notice it's still the blue side right here. That costs me $6 per foot. So okay, that side is going to cost me $6 per foot for y feet. And then on this one single red side here, that is y units long, that is going to cost me $18 per foot. So that's going to cost me $18 per foot for y feet. And of course I can clean this up then, just combine my like terms. C is equal to 12x plus 24y. So this is the function that I'm trying to, in this case, minimize here. I would like to minimize this cost. Now, we know how to find minima and maxima. We would say, okay, let's go find the derivative, find our critical points. We actually said exactly how we're going to do it up here. We said it's going to be in one of these two cases. But this is a little bit different here because I have these two, well, technically three variables. I have this function of two variables, which is a little bit more complicated than we're used to dealing with. So we need to come up with some other relationship between our two variables, x and y. See if we can simplify this. So hold on to this thought for now. We're going to come back to it in just a second. I would like to come up with some other relationship between x and y. So I'm going to go back and reread the problem. It says a fence is to be built to enclose a rectangular area of 800 square feet. Well, shoot, that seems important. I haven't used that 800 square feet. If I want to talk about the area of this rectangle, area is length times width, or in this case, x times y. So okay, I know my area is 800 equals x times y. This has a fancy name if you want to, again, impress your friends. This is called a constraint because we are constrained by the area of the fence. And what I'm going to do with this constraint equation is I'm going to solve it either for x or for y. It doesn't matter which one. You can pick whichever one you think is going to be easier. I think I will solve for x here just because. So I'm going to solve this equation for x, which means I need to divide both sides by y. So I have x equals 800 over y. So here's my constraint equation. Hopefully we kind of see a direction where this is going, because now what I can do is I can take out my x and replace it with 800 over y, and I'll have a function that is only in terms of y. I'll just have that one single variable, and then from there, that's something that we know how to deal with. So I'm going to go ahead and take my cost function, and let me see how much room I have. Oh boy, not very much. Okay, let me erase this right here. My cost function here is equal to 12x, that's 12 times 800 over y. I'm taking out that x and replacing it with 800 over y, plus 24y. So here I might take a moment and say, okay, I'm going to just simplify this before I start to take the derivative. So if I take 12 times 800, times 800, I should have 9600 over y plus 24y. And you could use the quotient rule here if you want, but hopefully you know by now that I just don't like using the quotient rule. So I'm going to write that as c equals 9600 y to the minus 1 power plus 24. So no matter what our domain looks like, we haven't really thought about our domain, and I'm going to come back at the end of the problem and think about that. No matter what our domain looks like, we still want to find our critical numbers. So that's what we want to do first here. Oops, I forgot my y. So I'm going to, first of all, take my derivative. So c prime is equal to 9600, negative 9600 when I multiply by negative 1, y to the minus 2 power plus 24, which of course I can write as negative 9600 over y squared plus 24. This is my derivative c prime. I would like to find the critical numbers, which means I need to find the values where my derivative is equal to 0 and where it does not exist. Here, so I'll take c prime, actually, let's do this, negative 9600 over y squared plus 24 equals 0. I'm going to solve this equation for y. So I will add this term over to the other side so that I have 24 equals 9600 over y squared. Multiply by y squared, I've got 24y squared equals 9600. So let's see, if I divide this by 24, I get a nice even 400. Y squared equals 400. Taking the square root gives me y equals plus or minus 20. So okay, I have two critical numbers here in positive and negative 20. We'll talk about which ones we want to pay attention to once we find the domain, but right now I just want to focus on finding the critical numbers. So we said we wanted to find the critical numbers, which means we took the derivative, set it equal to 0. Remember, we also want to think about places where c prime does not exist. Here in this case, I'm just going to take y squared, set that equal to 0, and that gives me y equals 0. So these appear to be my three critical numbers. I have 0, positive 20, and negative 20. So now what I want to do, I found my critical numbers. I want to find my domain, or sometimes I'll call it the interval of interest. And these are simply the values of y that make sense for our problem. So if I look at what y represents here, y represents some side of my rectangle. So if I think about, here, let me section this off. I'm going to think about, in a different color here, I'm going to think about the domain. It's a little bit confusing. I'm going to call it the domain of y, kind of the values that make sense for y. And I'll even write that in values that make sense for y. So the first question is, I'm going to ask almost every single time, do negative values make sense for your problem? Do negative values make sense for y? If y represents the side of a rectangle, no, y represents a distance. It can't be negative. So, okay, we're talking about 0, we're talking about positive numbers. The other thing I would ask yourself is, does it make sense if y is 0 here? Well, not really, because if y is 0, that means that these sides are 0. In that case, I don't really have a rectangle, I would just have a line. That's not particularly helpful. So the domain of y, this is all real positive numbers. So when we talk about the domain of y, we would say, well, we don't want to include 0, so we're going to use parentheses there. And we could choose really any positive number for y, and that would make sense. Some make more sense than others, definitely, but any positive number is doable here. So we're going to say 0 to positive infinity. And this is important because I want to determine whether we have an open interval or whether we have a closed interval. Here, I've identified that we have an open interval. We're working on 0 to infinity. We don't contain either of our endpoints. So now what I'm going to do is I'm going to go back and I'm going to look at the critical points that I found. First of all, 0. Well, 0 isn't in our interval. I'm just checking to see which critical points fall in our interval. 0 does not fall between 0 and positive infinity, which means we're not going to worry about it. Down here, we really had, let me separate these, we really had a positive 20 and we had a negative 20. Only one of those makes sense because we said we're really only considering positive numbers, so negative 20 doesn't make sense for our problem. So we have exactly this one single critical number, which is good. That's exactly what I want to see if we're working on an open interval. So we have our one single critical number. That's great news. Now we have just a couple more steps to do. I need to show that this critical number that I found right here, 20, actually results in a minimum. Because remember, at the very beginning of this problem, we said we want to minimize cost. We need to verify that we actually, in fact, have a minimum here. To do that, it's up to you. You can use either, for this one, the first derivative test or the second derivative test. I like the second derivative test, but that's just me. So I'm going to use the second derivative test now to show. So now I'm going to show that y equals 20 is a minimum. That's what I need to do next. So I'm going to look at, okay, here's my first derivative. I'm going to take the derivative of that guy. So c double prime is equal to, oh boy, let's see, I should have 9,600 times 2. That would give me 19,200, and that's a positive. Y to the minus 3 power, derivative of 24 is 0, so this is really 19,200 divided by y to the third. Now I'm going to do my second derivative test, which means I'm just going to take 20 and plug it into the second derivative that I've just found. So c double prime of 20 is equal to 19,200 divided by 20 to the third power. This will end up being 19,200 over, what would I have, 8,000, I believe. Which I don't really care so much what that number is. Remember, I really care about the sign of that number. This number's positive, which means that we have something which is concave upward. We have that minimum, which is exactly what we want. So yes, we do have a minimum. So we have verified that y equals 20 is a minimum. This is good. So we've shown using the second derivative test, we plugged this number in, we ended up with a positive number. We showed that we get a positive number, it's concave up, so y equals 20 has to be a minimum. It'd be really problematic for us if we wanted to minimize cost and, whoops, through some weird accident, I accidentally maximized our costs. I would probably be in big trouble in that case. So let's just check in with our problem. We just said that y equals 20 is a minimum. I'm going to go back and kind of find what I'm looking for. Let's just make sure that we answer the question here. So we wanted to, at the end of all of this, it said, find the dimensions of the rectangle that will allow for the most economical fence to be built. So I need the dimensions of the rectangle. So I need x and I need y. And I actually have half of that. I already have x. Excuse me, I already have y. I need to find x. So that means I need to find x. And there's a lot happening here. I kind of made this area too small to work. I'm sorry about that, but I need to find a relationship between x and y because I know that y equals 20 is a minimum. That's good. We have half of our answer. We just need to find the x value now. We'll look at right here. I have this relationship between x and y that we gave earlier. Always look back to your constraint equation once you've found the first dimension or the first important point here. So I know that x equals 800 over y. That's a relationship between x and y. So what that means for me is I can take y equals 20 and just plug that in. X equals 800 divided by y, so 800 divided by 20. That means that x should be 40. So that means the dimensions that will maximize my area here, or not maximize my area, minimize my cost. The dimensions that will minimize my cost are y equals 20 feet, and x equals 40 feet. So there's a lot happening in these problems. They are pretty involved. I think the hardest part about these is going to be getting this part set up, coming up with your objective function, coming up with your constraint function, creating your function that you can take the derivative of, and then finding the domain. Because a lot of that's up to you. I'm not going to tell you directly, here's your objective function, here's your cost function. A lot of times you need to go and find all of that information. So just to recap really quickly what we did here, just to recap the process here, I want to outline the steps just before we wrap this video up. So we drew this picture that represented our scenario. We said, okay, what are we trying to do? We figured out that we wanted to minimize cost. And we came up with a cost equation, and we simplified it right here. We have our cost equation, but we said, hey, that's in terms of x and y. I really only know how to work with one variable. So we came up with this other relationship between x and y and solved for one of our variables. Took that and plugged it into our cost equation. Once we had that, we said, okay, now we need to go and find our critical points. So we found our derivative. We found our critical points. We came up with 3 potential, 0, positive 20, and negative 20. But then we said, oh, we need to think about the domain. The domain here in this case would be 0 to positive infinity, and that eliminated 2 of my potential minimum values. Then we had to say, okay, y equals 20, that's the only critical number, that's good. I need to now show that this is a minimum, and I did that using the second derivative test. So you can use the first derivative test here if you would like. I just use the second derivative test just because that's my favorite. I showed that y equals 20 was a minimum, and then once I had y equals 20, I was able to go back to my constraint equation up here, plug in y equals 20, and find x is 40. If I wanted to know the cost, I could take both x and y and plug them into my cost equation. I could actually go and do that, but I wasn't asked to, so that seems like as good of a place as any to stop. So please take your time with these problems. There aren't too many in the homework. I want to say that there's less than 10 altogether. In the next few examples, we're going to be focusing more on business economic scenarios. So we're going to be looking at cost and profit and revenue and all of that good stuff.